All examples in this video are readily reproducible by simply downloading and running the alpha version of the Launch platform that is available online. The prototype is distributed under the MIT license for compatibility with the Pharo ecosystem, but the ports to other languages will most certainly use the GPL. We will begin with an expression language defined through multi-ordered grammars both here and here. These are both valid multi-ordered grammars recognized using the same algorithm, which is Gray. Their only difference is their choice of operators that can be lively edited and explored from within the environment. Some of you may have already noticed that the MOG rules are embedded within the syntax of the host language. This is already Launch at work, parsing both itself and its host language, or as this is usually described, Launch here is eating its own dog food. But I digress. The first example shows us a non-deterministic MOG rule. All alternatives are unordered, that can be used to explore ambiguities arising from the structure of the grammar. The parenthesized expression in the left has 5 alternatives in total that can be explored. 2 of them are readily accessible in the current configuration of the subtree. The other 3 can be viewed by navigating through the up and down arrows on the composite nodes of the left side. Similarly, the right parenthesis has 2 alternatives that can be explored, with a total of 10 alternatives for the whole expression. Notice here that these ambiguous alternatives essentially present us with all possible precedence and associativity configurations for the whole numerical expression. The correct and ambiguous definition for MOGs is seen in the second example using the recursively scoped operators that I have introduced. Addition, subtraction, and multiplication division alternatives are declared as simply recursive, which means that these alternatives are ordered and that any expression recursively invoked from within the subrules will continue from the alternative at the next line. This effectively makes the subrules left associative. Since expressions already include ordered alternatives, the rest of the rule is tainted with non-ordered subrules defaulting to self-recursion. This is the case for the exponentiation alternative, which by being self-recursive can, you guessed it, recurse on itself, which here has the effect of making the subrule right associative. If exponentiation was simply recursive, similarly to the other operators, we would get left associativity here too, a fact that we can readily and easily explore from within Launch. Finally, the grouping operator is recursively scoped, which means that the current parsing state is saved and the invocation of expressions from within parentheses will recurse from the top of the rule. We will discuss these operators in more details during the lectures. But what is interesting here to note is that we are able to incrementally and lively disambiguate the language without constraints on how the grammar is expressed and without resorting to external directives to avoid conflicts. In fact, in even more complex cases, we will shortly see that MOGs allow for a more intuitive definition than their PEG context-free or handwritten counterparts. Now, in order to turn our recognizers into compiler frontends, we need to bind our MOG rules to actions that produce some kind of intermediate representation. This is usually a cumbersome and time-consuming design step since language designers need to hard code and maintain all internal bookkeeping. This is where ASL, short for Abstract Syntax Language, comes in by providing an object-oriented solution for compile-time metaprogramming. Here is an example of a couple of short ASL actions producing the intermediate syntax tree for our expression grammar by reifying message sending or dynamic method invocation, if you prefer, into a first-class operator. Of course, apart from exploring MOGs with ParseView and generating ASTs with ASL and ParseEval, you can go ahead and evaluate your results with CompileEval and test them. Moreover, everything you've seen thus far can be expressed in a more organized way by subclassing the MOG recognizer, as we did here, defining your MOG rules as methods, then subclassing your recognizer to define the semantics of your language through ASL actions. All the facilities you used before to explore, visualize, lively execute, test, etc. are also supported for your class-based parsers as well. Moving on to more complicated examples that may exhibit multiple sources of ambiguity, we see here a simple procedural language exhibiting both the expression and the dangling else ambiguities, which we can go ahead and explore with parse view here and here. Notice how easy it is to disambiguate the conditional syntax of calc and define its semantics with ASL in just a couple of lines. Then we can get back to live testing, making sure we get the correct unambiguous result, inspect the bytecode produced, compile, evaluate, and test on the fly as we did before. Here is a variation of the collage algorithm implemented in calc, specifically designed to test the correctness of the conditional semantics for the dangling else cases. We will see more examples of ASL later on, but for now take a closer look at the classic postcard example of Smalltalk and its equivalent representation in ASL. ASL encapsulates the creation of ASTs through a familiar syntax that reifies the semantics of the underlying platform as metaprogramming operators for method creation, invocation, variable and literal definition, mutation, context manipulation, etc. This way the language designer can naturally express the compiled language semantics almost as easily as writing an interpreter. But instead of eagerly executing the result, the parser will produce an abstract syntax tree. The combination of mock rules with ASL is quite powerful, allowing you to describe real-world language semantics with clarity. Here is how you can describe the syntax and semantics of messages and message sends in Pharo using mogs and ASL, with recursion and ordering naturally defined. We will discuss this at length in the book and in the lectures, but these same rules are cumbersome to express in other formalisms, since the elaborate ordering of message sends has to be manually hard-coded. This is the case, for example, for other PEG-based, context-free based, or handwritten parsers for Smalltalk, and even for the definition of the language in the ANSI standard itself. Moreover, as we did before, we can go ahead and lively explore, parse, byte compile, and syntax highlight our new Pharo parser with ease.